is Mohammed Zamira. My roll number is 21951804A1. My subject is Signal Systems. My branch is ECB section. Today my topic is power spectral density of continuous time signals and its properties. Spectral density. The power spectrum S of x of a time series displays x of t describes the distribution of power into frequencies components composing that signal. According to Fourier analysis, any physical signal can be decomposed into a number of discrete frequencies or a spectrum of frequencies over a continuous range. The statistic average of a certain signal or sort of signals, including noise, has analyzed in terms of its frequencies content. It is called spectrum. When the energy of signal is concentrated around a finite time intervals, finite time intervals, especially it is if it is total energy is finite. One may compute the energy spectral density. The graph, the spectral density of a fluorescent light as a function of optical wavelength, shows peak at atomic transitions, indicates by the numbered arrow. The voice waveform over time left has a broad Audi power spectrum, right, more commonly used in the power spectral density or simple power spectrum, which applies a signal existing over all time or over a time period large enough, especially in relate the duration of a measurement, that it could as well as been over an infinite time interval. The power spectrum density PSD then refers to the spectral energy distribution that would be found per unit time, since the total energy of a signal over time would generally be infinite. Summation or integration of the spectral components yields the total power, or a special process or variance in a statistical process identical to what would be obtained by integrated display x power 2t over the time domain, as dictated by Parseval theorem. The spectrum of physical process x of t often contains essential information about the nature of, for instance, the pitch and timbre of a musical instruments are immediately determined from a spectral analysis. The color of a light source is determined by the spectrum of electromagnetic waves, electrical fields, E of t, as its fluence at an extremely high frequency. Obtain a spectrum from the time series, such as these involves the Fourier transformations and generalize based on Fourier analysis. In many cases, the time domain is not especially employed in practice, such as when a depressive prism is used to obtain a spectrum of light in a spectrograph, or when a sound is received through its effector on the auditory receptors of the inner ear, each of which is sensitive to a particular frequency. However, this article concentrates on situations in which the time series is known, at least in a statistical sense, or directly measured, such as by microphone sampled by a computer. The power spectrum study of stochastic process, as well as in many other branches of physics and engineering. Typically, the process is a function of time, but one can similarly discuss data in the spatial domain being decomposed in terms of spatial frequency. Explanations: any signal that can be represented as a variable that varies in times as a corresponding frequency spectrum. This includes familiar entities such as visible light preserved as a color, musical notes precede as pitch, ratio, or TV specified by their frequency or sometimes wavelength, and even the regular rotation of the earth. When these signals are viewed in the form of frequency spectrum, certain aspects of the received signals or the underlying process producing them are revealed. In some cases, the frequency spectrum may include a distinct peak corresponding to a sine wave component. And additional, there may be peak corresponding to harmonic of a fundamental peak. indicating a periodic signal which is not simply sinusoidal, or a continuous spectrum may show narrow frequency interval which are strongly enhanced corresponding to resonance or frequency intervals containing almost zero power as would be produced by a notch filter. In physical, the slight might be a wave, such an electromagnetic wave or a acoustic wave, or the vibration of a mechanism. The power spectral density (PSD) of the signal describes the power present in the signal as a function of frequency. A unit frequency power spectral density is commonly expressed in watts per hertz. When a signal is defined in terms only of a voltage, for instance, there is no unique power associated with the stated emulated amplitude. In this case, power is simply reckoned in terms of square of signals, as this would always be proportional to the actual power delivered by the signal into a given impedance. So one might use units of v square heads for the PSD, energy spectral density (ESD). Energy spectral density (ESD) would have units, would be v square headset, since energy has units of power multiplied by times. Example, watt hour. In general case, the units of PSD will be the ratio of units of variance per unit of frequency. So for example, a series of displacement values in meters over time in seconds will have PSD in units of meter squared by hertz, meter squared by hertz. In analyze of random vibration, units of g square heads or frequency used for PSD of acceleration, where g denotes the g force. Mathematically, it is not necessary to assign physical dimensions to signal or the independent variable. In the following discussion, the meaning of x of t, the meaning of x of t remains unspecified, but the independent variable will be assumed to be that of time. Energy spectral density, the function S bar x x of f, and the autocorrelations of display x of t, form of Fourier transformations, pairs or results, also known as Wiener-Kinch theorem, as a physical example of how one might measure the energy spectral density of a signal. Suppose represents the potential involves of electrical power plus propagating along a transmission line of impedance, uh, display Z, and suppose the line is terminated with a matched resistor, so that all of the pulse energy is delivered to the resistor, or and none is reflected. Total energy is found by integrated with respect to time over the duration of the pulse. To find the value of the energy spectral density, one could insert between the transmission line and resistor a band pass filter which passes only a narrow range of frequencies near the frequency of interest, and then measure the total energy dissipated across the resistor. The value of the energy spectral density uh, at display f is then estimated by, in this example, since the power has units of v square omega minus 1, the energy has units of v square omega minus 1 is equals to j. Hence, the estimated delta F of the energy spectral density has units of JHZ minus as required. In many situations, it is common to forget the steps of dividing by, so that the energy spectral density instead has units of V square Hz minus 2. More general similar techniques may be used to estimate a time varying spectral density. In this case, the time interval is finite rather than approaching infinite. This results is decreased spectral coverage and resolution, since frequencies of less than display 1 by t are not sampled, and results are at frequencies which are not an integrated multiple or no, and are not independent. Just using a single such time series, the estimated power will be very noisy. However, this can be elevated if it is possible to evaluate the expected values. The above For the above equation, using large or infinite number of short terms spectral corresponding to statistical examples of realizations of evaluated over the specified window. Note the signal estimate of the PSD can be obtained through a finite number of samples as before the actual PSD is achieved when approach infinite and the expected value is formally applied. In in a real world application, one would typically average a finite measurements PSD over many trials to obtain more accurate estimates of the theoretical PSD of the physical process underlying the individual measurements. This computed PSD in sometimes called a periodogram. This periodogram converges the true PSD has the number of estimated values. If two signals both possesses power spectral densities, then the cross spectral density can simulate be calculated as the PSD is related to the autorelations. So in the cross spectral density related to the cross relations. Properties of the power spectral density. The power spectrum is always real and non-negative. The spectrum of a real valued process is also an even function of frequency. For a continuous stochastic process x of t, the autocorrelation functions the autocorrelation functions R excess of t can be reconstructed from its power spectrum S of f by using the inverse power Fourier transform. Using a partial theorem, one can compute the variance. For a real process with the power spectral density, one can compute the integral spectrum or power spectrum distribution power content in frequency from DC to F using note the previous expressions from a total power in a special case where F is given to X estimation. The goal of spectral density estimation is to estimate the spectral density of a random signal from a sequence of time sample. Depending on what is known about the signal estimation sequence can involve parametric and non-parametric approach may be based on time domain or frequency domain. For example, a common parameter technique involves fitting observations of an autogression model. A common non-parametric technique is a periodogram. The spectral density is all usually estimated by using Fourier transformation methods, but other techniques such as maximum entropy method can be used. The spectral density or special in the midpoint of the spectral function, the frequency divided the distribution into two equal parts. The spectral edges frequencies usually expressed as EFX represents the frequency below which X presents of total power of given signals are located. Typically, X is the range 75 to 95. It is the proper particular a popular measure used in EEG monitoring. The spectral envelope is the enveloping curve of the spectral density. It describes one point in time. For example, in remote sensing using a spectrometer, the spectral envelope of a feature is the boundary of its spectral properties as defined by the range of brightness levels is each of the spectral bands of interest. The spectral density is a function of frequencies, not a function of time. However, the spectral density of a small window of a longer time signal may be calculated and plotted versus time associated with windows. Such a graph is called spectrogram. This is the basis of number of spectral techniques such as short time Fourier transformation and waveless spectral density. Sometimes an encounter amplitude spectral density asset, which is the square root of the PSD and ASD of voltage signals, has a signal of PSD since only in the case of the area under the curve magnification in terms of actual power over all frequencies or over a specified bandwidth. Electrical energy, the concept and use of power spectrum. The spectrum analysis measures the magnitude of this short time Fourier series for power spectral density. Climate science edit power spectral analysis have been used to examine the spatial structure of climate research. The results suggest atmospheric turbulence like climatic change to more local regional volatility in weather condition. Thank you for giving this wonderful opportunity.